Hello and welcome to today's GFG problem of the day. Hope you're doing well. So let's say today's problem, merge k sorted linked list. Okay, so what the problem is saying is we'll be given an array of n sorted linked list. Okay, and we want to merge them in such a way that after merging, there'll be a single linked list. After merging all this, so here are the n sorted linked list. There will be given an array, okay, of these n sorted linked list, and we want to merge this linked list into a single sorted linked list. For example, so all the resultant linked list look like 1, 2, 3, 4, 5. Okay, the element should be sorted. Okay, 5, 6, 7, and 8. Okay, so this is our resultant linked list. Okay, okay. So I hope you've got the problem. Now let's see the approaches to solve this problem. Okay, so first of all, we'll see the naive approach. Okay, the naive approach will be we will take at a time two linked lists, okay, in order to solve this problem. So at a time two linked lists, for example, L1 and L2. So what we're going to do, we are going to compare each node. We're going to compare each node, and whichever is lesser, we are going to add, okay, into the resultant linked list. Okay, so here, for example, one is smaller, then two, then three, then four, and then five, right? So this is out of this first step. So this is the list. Okay, then what we are going to do, we are going to take the next list. Okay, so 5 and 6. So we are going to again compare 1 and 5. So 1 is lesser, 2 and 5, 2 is lesser, 3 and 5, 3 is lesser, 4 and 5, 4 is lesser, 5 and 5 both are same. So we can take like either 1, 5 and 6. So this will be the next resultant list. Then we're going to compare this with 7 and 8. Okay. In this way, at every given point of time, we are going to compare two lists and we are going to form a resultant list. Okay. And then we are going to take the next list. So we are going to solve this problem in this way. Okay. But this is the naive approach. It is going to take what? O of, for example, if there are k number of linked lists, right? And we for each linked list, we want to iterate the n number of nodes. Okay. So the time complexity it is going to be of k into n. K is the number of linked list and n is the total number of nodes. Okay. And that is why the time complexity will be of k into n. Okay. Okay. Now let's see if we have some better approach. Okay. So let me erase this. So what we are going to do is, we are going to use the minimum heap, the property, the data structure minimum heap in order to solve this problem. So in Java and C++, the minimum heap we can implement using priority queue. Okay. So what we're going to do, we are going to take a priority queue. Okay. And we are going to set this priority queue so that it works as the minimum heap. Okay, it works as the minimum heap. Okay, so what is the property of minimum heap? So whenever you ingest elements, right? Whenever you ingest elements in the minimum heap, those are sorted in ascending order. That is, whenever you pull an element, so you will get the minimum element. Okay, so that's what we are going to do. For example, so first of all, we are going to store all the head nodes. Okay, all the head nodes in the priority queue. Okay, so what those will be? So, and also those will be sorted, right? In the minimum heap. Okay, 1 4, sorry, 1 4 5 and 7. So after ingesting all the, for example, if if the linked list was like this, right? LL, some, for example, 1 2 and 3. So while ingesting, we had ingested 4, 5, 7, and 1. Okay. But in the minimum heap, that will be sorted and it will be like 1, 4, 5, and 7. It will look like 1, 4, 5, and 7. Okay. So I hope you have got this. So now our priority queue looks like this. So we'll also create, for example, we'll create a dummy node. Okay. A dummy node. Okay. And that will be, so this is our dummy node. Okay. Which has what? Which has -1. Okay. So we have dummy, and we'll also assign a current pointer to this dummy node. Okay. Okay. So currently it is pointing to null. Okay. Currently it is pointing to null. So what we're going to do now, we'll iterate through this priority queue. We'll have a while loop until priority queue is not empty. So we will plug an element, and this priority queue, this minimum heap will return as the minimum element. So it will return -1. Okay. So what we're going to do here, after it returns -1, so we are going to assign current.next to this particular one. Okay. Okay. So, and we'll plug, since we have pulled this element out, right? So we will remove the element from the priority queue. We'll assign current.next to this particular plucked out node. Okay, so also we'll update our current. Now current will point here. Okay, current will point here. Okay, now also what we are going to do, we are going to whatever element we had fetched, right? Whatever node we had fetched, we will ingest, will check whether there exists the next node for it. Okay, so yes, definitely there exists a next node. So we are going to ingest 2 in this. So after ingesting 2, it will look like this: 2, 4, 5, and 7, right? 2, 4, 5, and 7. So this is our priority queue now. Okay, now again we'll do the same process. We will remove the minimum element. So 2 will be removed. Okay, 2 will be removed, and we'll go, this is the removed node. We'll check whether there exists the next node. Yes, there exists the next node, 3. Okay, so we're going to ingest 3. We're going to ingest 3. Now the priority queue will look like this: 3, 4, 5, 7. Okay, and also we are going to add this current dot next to this particular node too. Okay, we'll update our current. We'll update our current. Now again, we're going to remove the minimum element. Now this time it is 3. Okay, and we'll check whether 3 has next node. No, it does not have next node. So we'll just update current dot next to 3. Okay, so that it points. Okay, now current is this, right? And then we are going to again do the same process, fetch the minimum element, which is 4 this time. So 4, we're going to check whether 4 has next element. Yes, it has next node. So we are going to ingest 5. Okay, so so after this, how it is going to look like: 5, 5, and 7. Okay, since 4 next was 5, so we ingested 5 in this. Okay, now we'll update our current dot next to the removed node. Okay, so our current will also update the current. Okay, now this is our priority queue, the state of the priority queue. We will we will okay, we will remove an element 5. Okay, we'll remove an element 5. Okay, now we are going to check, does 5 has next? No, it does not have. So we are going to just add 5 to the current dot next. Okay, this is a 5, and we'll update our current, right? We'll update our current. Okay, then we'll remove the next 5. Again, we're going to check, yes, 5 is next. So we are going to ingest uh, the next element 6 comma 7. We will also ingest this 5, right? So we have our 5. Okay, so in this way we will solve a problem. Okay, I hope you've got the intuition. Okay, now also let's quickly discuss the time complexity. For example, if there are k linked lists, right? K linked list. Okay, k linked list. So in order to um, insert an element into the minimum heap, or remove an element from the minimum heap, it takes log k basically. So while log k, at every given point of time, there'll be k nodes in this minimum heap. You have seen, right? At any given point of time, there'll be k nodes in the minimum heap. So that is why. So in order to remove an element or ingest an element in a minimum heap of size k, it will require log k. Okay, and that is why the time complexity will be O of k log k. Okay, O of k log k. Now again, sorry. So here the linked list is k, but the total number will be, for example, let's say there are n nodes, right? There are n nodes, right? For example, with what I'm saying by n nodes. So anyways, we are iterating through all the n nodes. So these are the n nodes. N nodes are all the nodes of the given linked list, right? All the nodes of all linked list. Okay, and that is why the time complexity is going to be of n log k. N is the number of nodes, and to remove or insert an element into minimum heap of size k, it will take log k. Okay, so hence our time complexity is of n log k. Okay, so I hope you got the intuition. So I'll just request you, please subscribe to the channel, like the video. Okay, so first I'll implement the Java code followed by C++. Okay, so let's quickly implement priority queue. Okay, so since we are going to ingest or insert node, so we want to uh, tell the compiler, like we want to sort on what basis, right? We want to sort the minimum heap, or we want to create the minimum heap on what basis? So we want to create the minimum heap on the data, right? And the data in the node. So that's what we are saying. And we want to create a minimum heap. That is why a.data minus b.data. If you wanted to create max.heap, then we would have done b.data minus a.data. So this will make sure that the elements, the nodes are ingested in ascending order. Okay, are sorted in ascending order. Okay, so what we're going to do now, we are going to ingest the head. Okay, head nodes. Okay, pq dot add head. So we have ingested all the head nodes of all the linked lists. Okay, now what we're going to do, while pq is not empty. Okay, so what we're going to do here, so we will now remove the minimum node, right? From pq.poll. We'll now remove the minimum node. Okay. Now we are going to check here if, okay, before that, we also want to create the dummy node, dummy equal to new node -1. Okay. And we'll have a pointer current. Okay. Wherein we'll assign this dummy to current. Okay. Now what we're going to do, first of all, we're going to check if min node dot next is not equal to null. It is not equal to null, we'll ingest in the priority queue. Okay, in the minimum heap, min node dot next. Okay, now what we're going to do here, we'll also current dot next will insert, we'll assign minimum node to current dot next, then we'll say current equal to current dot next. Okay, in this way, we'll have our final uh, linked list. Okay, wherein dummy will be the first node, right? And we, since it is a dummy node, we want to return the dummy dot next. That's it. And this will give our resultant linked list. Okay. So you saw here, right? So we had formed this linked list. We had formed this linked list. Okay. So what we're going to do at the end, we are just going to return dummy dot next because dummy is -1, right? And next is what? So this is the next. So this is a new head. So we're going to return dummy dot next. Okay. So I hope you've got the solution. Now let's submit this. Okay. Thanks for watching. Please subscribe to the channel, like the video. Let's quickly see the C++ code as well. So here is the C++ code. So quickly I'll explain. So what we're doing here is, so we are creating priority queue and we are calling this compare function. Okay. Now what it does is by default in C++, in the priority queue, it is max heap. Okay. So we are like telling the compiler, okay, so how we need to create a minimum heap, right? How we need to create a minimum by saying that a dot data is greater than b dot data. That means if A has larger value than B, so A will be pushed down, further down, okay, and B will be up because we want to create minimum heap, right? Because B dot data is small and we want to create minimum heap, okay. So then what we're going to do, we are ingesting all the head nodes in the priority queue. Then we are creating dummy node. We are assigning dummy to the current pointer, and here we are having a while loop. Here we are removing the minimum element from the minimum heap. We are assigning minimum heap to next current dot next. Okay. And then so we are checking here if minimum node dot next it is not null pointer, then we are going to ingest in the priority queue. Okay. And finally we are returning dummy dot next. Okay. So I hope you got the solution. I'll also attach the code in the description section. Thanks for watching. I wish you a very happy, healthy, wealthy, and a great day. And also please don't forget to subscribe to the channel, like the video. Okay. Thank you so much.